Welcome to the first section of the harmonic measure. In this section, we're going to define the harmonic measure in the half plane, and we're going to extend our definition to the unit disk. So naturally, this section is divided into two parts. In the first part, we consider the half plane, and in the second part, we consider the unit disk. So let us start up with our construction on the upper half plane. So we denote H to be the sign of all Z in C such that the real part of Z is positive. So I'm so sorry, imaginary part of Z is positive. And we denote this for the upper half plane. And usually, R as usual is the real line. So now we suppose we have 2 points A and B lives in R such that A is smaller than B. So it makes sense to denote this as an interval A to B. And we consider a function theta, which is a function of z, and it is defined to be the argument of z minus b over z minus a. And by the definition of the argument functions, it is actually the imaginary part of the logarithm for z minus b over z minus a. So an observation tells us that this function theta is twice continuously differentiable and has zero Laplacian. So theta is harmonic on the upper half plane. And we see through the definition, theta is pi as long as z lives in the interval a to b, and theta is 0 outside the interval a and b. Okay, so now we're going to define a side E in the real line such that it can be written in the following form. E can be represented as the finite union of intervals where bj minus 1 is smaller than aj is smaller than bj. So that means these open intervals are mutually disjoint. So that is to say, AK, BK intersects AI, BI is empty for all K does not agree with I, and all these indices are legal. So now we define our theta j. So before we define our theta to be a harmonic function over the interval a to b. And now we have finitely many a to b, finitely many open intervals. So assigning the same index to theta, we can define our theta j to be the argument of z minus bj over z minus aj. Okay, so now, as before, we denote the value for theta j. So actually, these theta j's are only copies of theta, and each of these theta j are harmonic functions on the upper half plane. So just to be more precise, theta j equals to pi when z lives in a to b. aj bj. And theta j equals to 0 when z lives outside aj bj. Okay, so now we can define our harmonic measure. So the harmonic measure of a set E at a point Z is defined to be we denote it by omega ZEH, and it's defined to be summation j from 1 to n of theta j over pi. And we call this equation 1.1. And to be precise, we call omega ZEH the harmonic measure of a site, so actually for a site of finite union in the half plane. Okay, so we observe this harmonic measure. It has three arguments. The first argument is a point Z in some region H, and with respect to some site E. So actually, since Z is a point of the third parameter, sometimes we also write omega HZE. And when the underlying domain resists no confusions, we shall also denote it by omega ZE. But just to be precise, we shall always denote it by either omega HZ of E or in this form, because we do not want to risk of raising any confusions. Okay, so there's a reason, because for usual measures, they're only defined to be of one variables, and here we have a measure that is defined to be dependent on to two variables. And this is not a coincidence. It is actually designed to be in this way, or it happens to be in this way. Because the harmonic measure, as we shall see later, it is actually a transition density kernel. So that means it is one-sided a harmonic function and one-sided a measure. Actually, one-sided a Barrow probability measure. So I shall give some of the elementary properties for the harmonic measure on the half plane, and we shall expect these properties to be preserved every time we extend our definitions to a new region. So the first property, as I said before, is that the harmonic measure is greater than 0 and smaller than 1 for each point Z in H. So as I said, this harmonic measure is actually a transition density kernel, and one-sided it is a Barrow probability measure. But for this harmonic measure to be in that direction, a Barrow probability measure, it has to include both 0 and 1 into this display. So yes, they are included. So omega DEH, the harmonic measure, converges to 1 as Z lives in E. So this gives our upper bound. And for the lower bound, the harmonic measure converges to 0 as Z converges to the complement. So actually, to be more precise, I should denote it to some points. So Z converges to some zeta, and zeta lives in E. And here, let me denote by Z converges to some psi, where psi is a point in the complement of E, of the closure E. Okay, so if we draw a figure, so these parts are the upper half plane H, and for an arbitrary set E, this is E, and we denote this by our point Z. So as this point Z falls outside, then we know the value of this harmonic measure is 0, because by the definition of theta j, you see, once it falls outside these intervals, hence the set E, then it has value 0. And then by equation 1.1, it will be nothing but a finite sum of 0, which is 0. So when this point Z converges to some point in E, note that we do not consider the boundary points because E is not assumed to be closed. So when Z converges inside, then the value converges to exactly 1. So again, for the third property, as Z goes outside, once it reaches to the boundary point, because E needs now to be closed. That is to say, the E needs now to equal to its closure. So for that case, this point Z happens to happens. So in this case, Z happens to be a point on the closure. So in this case, it is still converges to 1 as suggested by the second property. But as long as Z exits the boundary, then it's going to have a value 0. So this is part of the reason why using Brownian motion is a very natural way to interpret the potential theory or harmonic measure because of this very, very specific property. Okay, so now know that the harmonic function, the harmonic measure omega z e h is the unique harmonic function on the upper half plane satisfying 1, 2, and 3. So for at the first glance, it may be a little weird to call a measure, harmonic measure, a harmonic function. But as we said earlier, that a harmonic measure is one-sided a harmonic function and one-sided a probability measure. So as long as we encounter that transition kernel terminology, we're going to be very this statement will be very clear. Okay, so instead of giving so we postpone the interpretation to later discussion, but we can prove the uniqueness, and the uniqueness is the Lindelöf's maximum principle. So we suppose the function u of z is harmonic and bounded. We mean bounded above on a region omega, such that omega is not too big, for which we mean the closure of omega does not equal to the complex plane. And if we let f be a finite subset on the boundary of omega, and if the limit sup as z goes to zeta, u of z is smaller or equal to 0 for each zeta lives in boundary omega minus f. We call this equation 1.2. Then u of z is smaller or equal to 0 on the entire omega. And this result is called Lindelöf maximum principle. So we first interpret this result. Again, we're working with a complex plane, and we consider this to be our omega. And of course, omega, actually, I can just denote it by omega bar, because in this time, by assumption, omega bar is not the whole complex plane. And f is a finite subset on the boundary. So I can draw So we call F1, F2, F3, and F4, and denote our F to be union of all Fi's, Fj's. So if for every zeta on some point, so this zeta, 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 arbitrary, and harmonic functions, they're all smaller or equal to 0 on these points, then u of z is smaller equal to 0 on entire omega. So this result tells us that a local upper bound can be extended to a global upper bound. Okay, so let us prove this result. So we first make an observation. If we fix some z naught, a point that is not in the closure, then this might z minus z naught take the reciprocal. It transforms omega into a bounded region. So if one is familiar with the complex analysis, then one can realize that this function is actually a Mobius transformation or an inversion. So if we draw a figure, so this is zeta naught, and for some z, for example, this is very big, but you take the reciprocal, it is going to lie inside the unit disk. So that is how the inversion or the Mobius transformation works. So we can transform unbounded region to a bounded region. So without loss of generality, we can assume omega is bounded. Okay, so now if 1.2 holds for all zeta in the boundary, then this is nothing but the usual, actually the ordinary maximum principle. Okay, so so our Lindelof maximum principle is stronger than the usual ordinary maximum principle for subharmonic function or superharmonic functions. Okay, so but know that in our assumption, zeta is not cannot be chosen arbitrarily on the boundary of omega, but in boundary omega minus a finite subset. But that's okay. So since f is assumed to be a finite subset, we can denote by f equals to zeta 1 up to zeta n, and we can choose epsilon greater than 0, and we can cite a function u epsilon of z is defined to be u of z minus epsilon times the summation j from 1 to big N. Take the logarithm of the diameter of omega minus z minus theta j. Okay, so observe that u of z is harmonic, and inside this dude is harmonic, and a finite linear combination of harmonic function is harmonic. So u epsilon of z is nothing but n plus 1 many linear combinations. So it is harmonic. Then u epsilon is harmonic on omega. And by our assumption, we have the lim sup at z goes to zeta u of z. U epsilon of z is smaller or equal to 0 for each zeta. lives in the boundary. So therefore, our u epsilon of z, u epsilon is greater, small equal to 0 for all epsilon greater than 0. So finally, since epsilon is chosen arbitrary, we can let epsilon go down to 0 and 1 gets u of z. So by the definition of u epsilon of z and the fact that lim sup u epsilon of z is smaller or equal to 0, then we see that u of z is smaller or equal to the limit as epsilon goes down to 0 of epsilon j from 1 to n logarithm the diameter of omega over z minus theta j. And since epsilon is going down to 0, this is 0. So we have established the inequality u of z is smaller or equal to 0, and actually this because we are assuming 1.2, and we can see that indeed it is indeed this is how we define, because this epsilon part is the tail for pointing f. So this proves our result when zeta lives in the boundary of omega minus I. So we're done. Okay, so this summarizes the first part of this section 1.1. And in the next part, we're going to extend our definition for harmonic function to the unit disk. Thank you for watching, and see you in the next video.